Okay, so welcome to this short video for EGB242. So my name is Dr. Elliot Carr, and I'm a lecturer in applied and computational mathematics within the School of Mathematical Sciences at QUT. So in this unit, I'm going to be teaching the maths component. So I'm going to be teaching the maths component of EGB242. And the purpose of this video is to revise some of the crucial and fundamental mathematical skills required for EGB242. Okay, so we're going to start off with the exponential function. Okay, so an incredibly important mathematical constant in mathematics is Euler's number. Okay, so Euler's number is represented by a lowercase e, okay, and its value is given by this value here, so it's 2.718, so on. Okay, and these digits repeat forever. Okay, and Euler's number is an irrational number. Okay, so that means that it cannot be expressed as a rational number. So it can't be expressed in the form a on b, where a and b are integers. Okay, and this number is very special because if I take this number and raise it to the power of x, okay, and consider the function e to the x, this is a special function because it's the only function in mathematics whose derivative is itself for all x. Okay, so if I take the derivative of e to the x with respect to x, I get the same function back. Okay, and because of this property, this function e to the x pops up all over mathematics. Okay, it has numerous applications in mathematical modeling of physical processes because of this property. And because of this property, it's often called, and because of its, because it appears throughout mathematics, it's often called the most important function in mathematics. Okay, so one property of Euler's number is that it exhibits this power series expansion. Okay, so e to the x is precisely equal to this summation. So the sum from k equals 0 to infinity of x to the k over k factorial. Okay, now you recall that k factorial is defined in the following manner. Okay, so it's defined for an integer or a whole number, k, and basically it's defined by multiplying k by every integer smaller than it and itself until I get to 1. Okay, so k factorial is k multiplied by k minus 1 multiplied by k minus 2. Continue to do that until I get to 1. Okay, so for example, 3 factorial is 3 multiplied by 2 multiplied by 1, which is 6. Okay, and by definition, 0 factorial is equal to 1. Okay, so if we look at this series expansion, and if I take the first term, which is k equals 0, then I get x to the power of 0 over 0 factorial. Okay, now x to the 0 is 1 for all x, and by definition 0 factorial is 1, okay, whoops, and 1 divided 1 is equal to 1, okay, so that gives me my first term for k equals 0. Okay, and it turns out that this power series expansion is simply the Taylor series of e to the x. Okay, now the Taylor series of e to the x, so if I define f of x equal to e to the x, then the Taylor series about x equals 0 is defined as f at 0 plus f dash at 0 times x plus f double dash at 0 times x squared on 2 plus dot 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 and so on. Okay, now because the derivative of e to the x is itself, the second derivative, which is the derivative of e to the x again with respect to x, is itself. Okay, I evaluate each of these at x equals 0. Okay, as appears in my Taylor series. Okay, so all of these are going to be equal to 1. Okay, so I get 1 plus x plus 1 on 2 factorial x squared. Okay, I continue to do that and I get precisely this formula up here. Okay, so here is what the graph of e to the x looks like. Okay, so I can think of this as a plot of the function y is equal to e to the x. So this is the y-axis, this is the x-axis. Okay, so at x equals 0, which is this point, e to the x, e to the 0 is 1. Okay, so my function passes through this point. Okay, and the slope, because the derivative of e to the x is itself, okay, at every point along the function, the slope, okay, so say this is the point A, x equals A. Okay, so this value here is f at A, or e to the A. The slope of the tangent line so the slope of this line is also e to the A, okay, because of this property of the exponential function. Okay, so we can look at taking the first few terms of this power series expansion. So I can approximate e to the x by just the first term of this power series. So I can approximate it by just the value of 1. Okay, so I can do that. I get a good approximation at x equals 0. Okay, but everywhere else the approximation of the blue curve to the black curve is poor. Okay, but I can continue to take more terms, so I can take 2 terms, approximate e to the x by 1 plus x. Okay, I do that. So now I'm matching both the solution value and the derivative at this point. Okay, so the slope of this red line is equal to the slope of the black line at this point x equals 0. Okay, so that's a property of the Taylor series. Okay, and I continue to do that and take more terms. So take the next term, the x squared term, I get a better approximation to e to the x. I take the cubed term, I get an even better approximation. Okay, and eventually you take more and more terms, the approximating curve is going to coincide precisely with the black curve, y equals e to the x. Okay, so we can use this power series of e to the x to verify that the derivative of e to the x is itself. Okay, so remember we have e to the x is equal to 1 plus x plus x squared on 2 factorial plus x cubed on 3 factorial plus ... Okay, now I'm going to differentiate each individual term of this series. Okay, and to do that I'm going to use the property that the derivative of a monomial, x to the power of n, where n is an integer, is equal to, I take the power down and I take 1 from the power. Okay, so d okay, so the derivative of e to the x, derivative of 1 is 0, derivative of x is 1. Now the derivative of x squared, I bring the 2 to the front and take 1 from the power. So I get 2x to the 2 minus 1, which is 1, over 2 factorial. Derivative of x cubed is 3x squared over 3 factorial. Okay, so the 0 just goes, so I get 1 plus 2x. Now 2 factorial is 2 times 1. Three factorial is 3 times 2 times 1. Okay, so these 2's are going to cancel, the 3's will cancel. Okay, so I'm going to be left with 1 plus x plus x squared over 2 times 1, which is just 2 factorial. Okay, so I precisely get back this expression here. Okay, so the derivative of e to the x is equal to e to the x. Okay, so one important application of the exponential function is that because its derivative is itself, it finds application in solving differential equations. Okay, so in first year, in MZB126, you would have used exponential functions to solve ODEs. Okay, so ordinary differential equations. So you would have used exponential functions to solve ODEs of this form. So the problem is find the function x such that when I differentiate it with respect to t, I get alpha times the original function back. Okay, and it turns out that the solution of this problem is x equals, for any constant c, multiplied by e to the alpha t. Okay, and that's because dx dt of this function, differentiating the exponential, the alpha comes out the front. Okay, so the derivative is just given by that, and that's simply equal to alpha x. Okay, so that satisfies this differential equation. Okay, so that's a very simple example. You would have also used exponential functions to solve more complicated ODEs. Okay, so this is a first order. This one here is a first order differential equation. Okay, because the highest power in the derivative is 1, whereas this is a second order because we have second order derivatives are the highest power. Okay, so we can also use exponential functions to solve differential equations of this form. Okay, and they always, so this is an example of a linear constant coefficient ODE. So it's constant coefficient because the coefficients in front of the derivatives are just constants. They don't depend on y and they don't depend on t. Okay, so in this case the constants are just 1, 1, and 1. Okay, and we can always use exponentials to solve ordinary differential equations in this form. Okay, so we're going to show you how to do that for this ODE. Okay, so basically we seek a solution of the form e to the mt, where m is some unknown constant, but we determine it during the solution procedure. Okay, so just need to figure out how to add a page. Okay, this is it. Okay, so example 2. Okay, so we're going to let the solution take the form e to the mt. Okay, and I want to substitute. Okay, so I'll just write down my differential equation. So it was d squared y dt squared plus dy dt plus y equals 0. Okay, so I want to substitute this function into this differential equation and then determine what the value of m is that satisfies the equation. Okay, so to do that I need to find the first derivative, okay, and the second derivative of y. Okay, so dy dt is just me to the mt, and d squared y dt squared. So the second derivative of y with respect to t is m squared e to the mt. Okay, so substituting into my ordinary differential equation. Okay, so I get m squared e to the mt plus m e to the mt plus e to the mt equals 0. Okay, so this expression on the left-hand side, I can factor out e to the mt. Okay, and what I'm left with is m squared plus m plus 1 equals 0. Okay, e to the mt, for any t, is always greater than 0. Okay, the exponential function is always greater than 0, so it's not equal to 0, so I can cancel it from both sides. So I can divide through by e to the mt, so that effectively removes the exponential. Okay, so what I want to solve is this equation, m squared plus m plus 1 equals 0. Okay, so to do that, I can use the quadratic formula. Okay, so m is equal to negative b, which is the coefficient of the m term. So negative 1 plus or minus the square root of b squared, so 1 squared, minus 4 times a, which is the coefficient of m squared, which is 1, times c, which is the constant term, which is also 1. Divided by 2 multiplied by a, which is 1. Okay, so this is equal to negative 1 plus or minus, so underneath the square root sign I have 1 minus 4. Okay, so that's the square root of negative 3 over 2. Okay, so I've got the square root of a negative number, so I'm going to get an imaginary number here. So I'm going to get root 3 of j over 2. Okay, so remember j is equal to square root of negative 1, or j squared is equal to negative 1. Okay, so I have my two roots of my quadratic equation. Okay, so I effectively have two values of m that satisfy this equation. Okay, so therefore both y1 equal to, so y is equal to e to the first root, which is, I'm going to take the plus sign, so negative 1 so negative a half plus root 3 on 2j multiplied by t is a solution, and the other root, so e to the negative a half minus root 3j is also a solution. Okay, so this is a nice segue into the next topic we're going to be talking about, which is complex numbers. Okay, so we just saw the use of complex numbers in the solution of differential equations. So complex numbers are going to be very useful throughout this unit. Okay, so it's important that you understand the basics of complex numbers from earlier units in first year. Okay, so by definition, as we saw in the previous example, the imaginary unit j is defined equal to the square root of -1. Okay, so by definition, if I square both sides, I get j squared equals, if I square the square root, those are going to cancel each other out and I get -1. Okay, so j is defined as the square root of -1, or equivalently j squared equals -1. Okay, and a complex number is any number z which takes this form. Okay, so I can have any, so where a and b are real numbers. Okay, so z equals a plus bj for any values of a and b. Okay, and if I define the set of complex numbers, then this is, so the set of all complex numbers is the set of all numbers in this form, z equals a plus bj, for all a and b an element of the reals. Okay, and complex numbers behave very similarly to vectors in R2 or in 2D. Okay, so to see why that is the case, we can plot in the complex plane so say if we had some number z equals a plus bj, okay, and this axis is the real part of z, and this is the imaginary part of z. Okay, so for z equals a plus bj, the real part of z is equal to a, and the imaginary part of z is the coefficient of j, which is equal to b. Okay, so this point is equal to a along the real axis, and it's equal to b along the imaginary axis. Okay, and this feels very much like a vector, because if we connect from the origin to our complex number, this feels very much like a vector z equals ab. Okay, so complex numbers and vectors behave in some respects very similarly. Okay, so now we're going to look at multiplying and dividing and adding and subtracting complex numbers. Okay, so if I've got two complex numbers, z1 and z2, so z1 is equal to x plus yj, z2 is equal to v plus wj, and to add the two vectors, to add the two complex numbers together, I add the real parts together, so x plus v, and I add the imaginary parts together, y plus w. Subtract, I subtract the real parts, and I subtract the imaginary parts. Okay, so multiplying, so I can also multiply two complex numbers together, and to do that it's very similar to expanding expressions. So I expand the brackets as so. Okay, so the first term is x times v, the second term is x times wj, which is xwj, the third term is yj times v, which is yvj, and the fourth term is yj times wj, which is ywj squared. Okay, and then using the fact that j squared is equal to -1, okay, I get this term, and then I can combine the real part and then the imaginary part. Okay, so now this is in the form of a complex number, z equals a plus bj, where a and b are real numbers. Okay, so dividing two complex numbers is a little bit more tricky than multiplying. And to do this, we need another tool which is known as the complex conjugate. Okay, so by definition, the complex conjugate, or the conjugate of a complex number, z equals x plus yj, is defined as, so the notation is z asterisk, raised to the power of an asterisk, and all we do is change the sign. So whatever the sign is for the original complex number, we change it. So the plus becomes a minus. Okay, now if we multiply z by its conjugate, or do the reverse, multiply the conjugate by z, okay, we always get a real number. Okay, and to see why, so z times z conjugate is equal to x plus yj times x minus yj. Okay, so I'm going to do my expanding again. So x times x is x squared. X times negative yj is negative xyj. Yj times x is plus xyj. And yj times negative yj is negative y squared j squared. Okay, so this is going to simplify. These two terms cancel. The j squared becomes a -1, so this becomes x plus y squared. Okay, and x and y are both real numbers. Okay, so this is a real number. Okay, so this is exactly what we just did. Okay, this result is a consequence of this difference of two squares, which is classical in algebra. Okay, so to divide two complex numbers, what we do is multiply by the conjugate of the denominator. Okay, so the denominator is z2. Okay, so I multiply the numerator by the conjugate of z2 and the denominator by the conjugate of z2. Okay, so in this example, z2 is equal to v plus yj, so the conjugate, I change the sign on the imaginary component, so v minus wj, and multiply the numerator and the denominator by that. Okay, and then if I go through and expand my brackets, okay, and do that on the top, and the bottom, okay, what I end up with is this result. Okay, so the idea is to express this in the form of a complex number, which is a plus bj. Okay, and this is in that form because I can write this as xv plus yw over v squared plus w squared plus yv minus xw over v squared plus w squared multiplied by j. Okay, so this is in the form of a complex number, a plus bj, okay, because this is a real number, this is a real number. Okay, so a function that we're going to see a lot throughout this unit is a sinusoidal function. Okay, so we're going to be talking a lot about sinusoidal waves. Okay, and these are waves that can be expressed as functions in this form, so a sine function. Okay, where A is known as the amplitude, F0 is the frequency, and phi is the phase shift. Okay, so there's an applet here which basically illustrates the effect of altering each of these parameters. So altering A, altering F0, and altering phi, what effect that has on the function. So I'm just going to open that and have a little play with that. Okay, so I want to get it into the form of the function that's on the slide. Okay, so that function has a plus phi, so I'm just going to change that to a plus. Okay, so these sliders basically allow us to control the values of the different parameters and see what effect it has on the function. Okay, so this function has a classical sinusoidal shape, so the shape of a sine function. Okay, so if I modify A, so if I increase A, which is the amplitude, that increases the height of the peaks. Okay, so it increases the distance from the x-axis to the height of the peak. Whereas F is the frequency, and if I increase F, then the frequency increases, so I get more oscillations occurring in a given length. Whereas phi is the phase shift. Okay, so a phase shift of 0, my function will start at the point 0. Okay, so at t equals 0, the value will be equal to 0, or at x equals 0 in this case. Now if I have a positive phase shift, then that moves the function to the left, and if I have a negative phase shift, then that moves the function to the right. Okay, so you can have a little play around with this in your own time. So I'll just go back to the slides now. So another important concept in sinusoidal signals is the relationship between the time delay and the phase shift. Okay, so if we have a time delay given by capital T, okay, so basically what I do is evaluate my function S at t minus capital T, where t represents the time delay. Okay, so I just substitute that into my function. Okay, so all I'm doing is replacing t with t minus capital T. Okay, and I can then expand and group the terms together, and this becomes my new phase shift. So this basically tells me the effect that a time delay has on the phase shift. So basically what it does is it'll shift the phase shift by negative 2 pi times the frequency times the time delay. Okay, so when working with these sorts of trigonometric functions, it's often useful to use some of these trig identities, and this is particularly useful, as we'll see, I think in the first lecture. These are useful for calculating some integrals. Okay, so basically these are just identities that relate, for example, the cos of the sum of two angles and the sine of the sum of two angles, okay, as well as a minus b and a and sine of a minus b. Okay, so it basically tells you how to relate these expressions in terms of just the classical sine A, cos A, sine B, and cos B. Okay, and we can also deduce different formulas. So for example, this one, if I take cos of A plus B and add to it cos of A minus B, okay, then these two terms are going to cancel and I get two lots of these terms. Okay, so I get 2 cos A, cos B. Okay, so you can have a look at these, and we're probably going to use a few of these throughout this unit. Okay, so a very important part of EGB242 is integrating by parts. Okay, so integration by parts is basically a method for integrating a product of two functions. Okay, so the formula for integration by parts, so we have a product of two functions. So my two functions are u and v dash. Now the integration by parts formula tells me that the integral of uv dash with respect to x is equal to uv minus the integral of vu dash. Okay, so the basic procedure is to firstly identify what function I'm going to call u and what function I'm going to call v dash. Okay, and normally what you do is set the one that is easier to integrate to be v dash, or set the one that gets simpler after differentiating, okay, to be v. Okay, and that's because when I differentiate u, I get u dash, which appears in the next integral that I have to do. Okay, so we're just going to do an example now of integration by parts. Okay, so I'm going to do example 3, and then I'm going to let you have a go at doing example 4 before the first week, or before the week 1 lecture, and I'm going to cover this example in week 1. Okay, so I'm going to do example 3. Okay, so we want to integrate x times cos x with respect to x. Okay, so what I first need to do is identify what u is equal to and what v dash is equal to. Okay, because remember my formula is the integral of u v dash is equal to uv minus the integral of vu dash dx. Okay, so I'm going to choose u to be equal to x, okay, and that's because the derivative of x is simple, it's just equal to 1. Okay, so that's going to give me a simple integral to compute over here, and hopefully we can get a final answer. Okay, so I'm going to set u is equal to x and v dash equals cos x. Okay, so I need u dash in my formula, which is equal to 1, and I need v. So v is the integral of v dash, okay, and the integral of cos x is sine of x. Okay, so hence the integral of x cos x dx is equal to uv minus the integral of v u dash dx. Okay, so uv is x sine x minus the integral of v times u dash, which is the integral of sine x. Okay, so I've got a simple integral here to do. I just need to integrate sine of x, and I know what that is because it's equal to negative cos x. Okay, so my choice of u and v dash has worked for this particular example. Now if I got a more complicated integral here, then I would reverse my choice of u and v dash. Okay, so this is x sine of x plus x, sorry, the integral of sine x is negative cos of x, so the negatives, two negatives are going to be a positive, I get cos of x. Okay, and plus c, which is just the constant of integration. Okay, so as I said before, example 4, have a go. Yourself, and I will do this in week 1 lecture. Okay, so another important concept that I want to talk about in this video is how to relate the unit circle to trigonometric functions. Okay, so the unit circle okay, so I have my usual axes. So the unit circle is just the circle of radius 1 centered at 0. So this is the circle of radius 1 centered at 0. Now because this has radius 1, this point here, so the x value is 1, the y value is 0. Here the x value is 0, the y value is 1. At this point, x is equal to 0, y is equal to negative 1, and at this point x is equal to negative 1, y is equal to 0. Okay, so just, I know this doesn't quite look like it, but just imagine that this is a circle of radius 1 centered at the point x equals 0. Okay, so if I have some point on this circle with coordinate x and y, then the x value and the y value is just equal to, so x is equal to cos theta, y is equal to sine theta, okay, where theta is this angle in here. Okay, so I can use this unit circle to calculate sine and cos of various common fractions of pi. Okay, so recall that pi on 2 is equal to 90 degrees, so a theta value of 90 degrees. Okay, so this is pi on 2. This is pi. This is an angle of 0 or 2 pi. Okay, this is pi or negative pi. And this is 3 pi on 2 or negative pi on 2. Okay, so for example, if I want to know what cos of pi on 2 is, then I just need to think about this unit circle. Okay, so pi on 2 is up here. I know that cos is always the x coordinate. Okay, so cos of pi on 2 is 0. Sine of pi on 2 is the y coordinate, so it's equal to 1. Okay, similarly, cos of pi is the x coordinate. Pi is equal to 180 degrees. Okay, so 180 degrees through here. So cos of pi is equal to the x coordinate, which is -1. Sine of pi is the y coordinate, which is equal to 0. Okay, so we can use this unit circle to tell us what the value of trigonometric functions cos and sine are at common fractions of pi. Okay, so just to finish off this video, I'm going to talk about geometric series. Okay, so we're going to be talking quite a bit about series, particular Fourier series in this unit. Okay, so it's important that you have an understanding of what a series is. So one common example of a series is a geometric series. Okay, so the geometric series is basically a series where the ratio of two consecutive terms is constant. Okay, so for this particular series, the ratio of each term to its previous term is r. Okay, so I have 1, the second term is r, so r divided 1 is r. The third term divided by the second term, r squared divided by r is r. And then the fourth term will be r cubed. R cubed divided r squared is also r. Okay, so a geometric series satisfies the property that the ratio of two successive terms is a constant throughout the summation. Okay, so for this geometric series, we have some nice elegant results for calculating what the sum is equal to. So working out what this summation is equal to for any n. We have a nice elegant formula for doing that. Okay, so this slide, just to finish off, provides a quick derivation of that formula. Okay, so basically what you do is if you consider the term Sn, okay, so that's the sum for a value of n, and multiply that by r, okay, so all I've done is use my expression for Sn, and I'm going to multiply that by r. Okay, so expanding these brackets, okay, so I get this term, so each term just increases by the power of r. Okay, then I can subtract this away from Sn. Okay, so this is Sn minus r Sn. Okay, so this term here is just Sn, this term here is r Sn. Okay, and if I do that, what I notice is that all the terms cancel except for the first term in Sn and the last term in rsn. Okay, so the r's cancel, the r squareds cancel, all these terms cancel, the rn's cancel, and all I'm left with is 1 minus r to the power of n plus 1. Okay, so then I can divide through by 1 minus r, okay, and I get my formula for the sum of a geometric series. Okay, and if I wanted to look at what this sums to as n goes to infinity, now provided r is between -1 and 1, okay, so r is less than 1 and greater than -1, okay, this should just be an absolute value, then provided this is the case, then this term r to the n plus 1 will go to 0 in the limit as n goes to infinity. Okay, so the limit as n goes to infinity of r to the n plus 1 is equal to 0, provided this holds. Okay, so this term goes to 0, so I'm just left with 1 on the numerator, 1 minus r on the denominator. Okay, so this is just an elegant result for the sum of an infinite geometric progression. Okay, so just to finish off, there's quite a nice link here that talks about geometric progressions and kind of explains them visually. Okay, so this is a geometric progression with r is equal to 1/2. So if I look at the first few terms of this summation, so I get 1/2. So n equals 1, I get 1/2. N equals 2, I get 2 squared, 1 on 2 squared, which is 4. Okay, I keep doing that for n equals 3, n equals 4, n equals 5. Okay, so if I consider a unit square, so a square of length 1, then 1/2 of that obviously looks like this. I want to add 1/4 of that to it, add 1/8. Okay, add 1/16, add 32, and so on. Obviously this is going to just keep on approaching the value of 1. Okay, and that's because of this formula. So with r equals hang on, Okay, so r equals a half in here, in this formula, then I get 1 minus a half, 1 over that, which is 1 over 1/2, which is 2. Okay, so why is that different? Okay, that's because it doesn't contain, yeah, okay, so the answer is, this summation started at a half, it didn't start at 1, okay, so the limit of this is equal to 1, whereas if we start at 1, then the limit is equal to 2. Okay, so that basically concludes this short video about the fundamental concepts, or fundamental mathematical concepts for EGB242. Okay, so as I mentioned previously, please have a go at example 4, and please have a go at this yourself, and I'll present the solution in next week's lecture. Okay, so I look forward to seeing you all in week 1. Thank you.